Hello guys and welcome back to my channel Civil Construction and Tutor, and in this video we will be modeling and analyzing a circular water tank. We can also say this as a source shaft for now because I'm basically modeling and analyzing a source shaft. So the basic idea is same, that it will hold the water and it will be subjected to different loads such as earth pressure from the outer phase and internal hydrostatic pressure in the inner side of the wall, and similarly it will be subjected to earthquake load, and the base of the source slab, that is the slab, will be subjected to, so this is basically the slab, and it will be subjected to the dead load of the earth, that is soil, which is resting on this projection. And you can also see that the thickness varies. So at the base the thickness will be maximum, then we can subsequently reduce the thickness considering that the pressure of the water, that is the hydrostatic pressure, will reduce along its height. So firstly we will calculate the width of the footing, or we can say simply the width of the slab that is required to avoid the bearing pressure failure. So for now, to calculate the bearing pressure, we will compute considering this whole dead load of the structure, water load only. We will not consider the earthquake load because according to the code, that is the IS code I have already mentioned before also, if the earthquake load or wind load does not exceed 25% of the dead load, it is not necessary to include the effect of earthquake. So for the horizontal seismic coefficient, we have formula as Zi into Sa by G, that is Zi Sa by 2Rg. So where Z is the zoning factor and 0.36 for zone 5 considering IS 1893 code. Similarly, importance factor will consider 1.5 as it is an important structure, and the value of R will be considered 4 for ductile RC structural wall, and Sa by Z. So since the time period will come less than 0.1 second, so it will be 2.5 considering these all parameters. So the design horizontal seismic coefficient comes as 0.168 only, which is less than 0.25. So we can avoid earthquake load for calculating the foundation width. So that means we have to compute the bearing pressure with respect to dead load and water load only. So firstly we will compute the dead load, and for this I have prepared an Excel sheet, and this is the drawing that we are going to use for the modeling and analysis. So this is an section of the water tank, and you can see the RL value. So from this we can compute the height of the structure, and similarly this is the water level, and this is the maximum water level, and this is the minimum water level. So these are the different different factors that we have to consider for calculating the water height. And similarly this is the normal, or this is the existing ground surface level or ground level profile. For now the backfill has been proposed up to this level only, so that means soil here is capable of holding or resisting this much of soil load without any failure. So we don't have to include the weight of the soil while calculating the width of the base slab. So if the soil was capable of resisting this much of soil weight, then obviously it will hold this much soil. Similarly, as you can see, the wall is being tapered, that is up to certain point the wall thickness is more. Similarly, after this point the wall width or the wall width thickness is being reduced because the effect of the hydrostatic pressure will be less, and the plus point of reducing this wall thickness will be that the seismic weight of the structure will reduce, and hence the effect of earthquake also decreases. So we have to consider that point as well. As you can see here, the internal diameter of the structure is 8.5, that is the clear diameter of the structure, and these are other diameter considering the wall thickness. So for top it is 9, and at base considering the wall thickness as 1 meter, it comes as 10.5. So 1 meter for this wall and 1 meter for this wall, then 8.5 plus 1 plus 1, 10.50. So for now the initial sizing is 1 meter. So we'll check whether it is required or not. Now for calculating the dead load, we'll consider all the parameters. So here I have prepared an Excel sheet and we'll compute the dead load. So let me take this. So firstly wall, so we'll consider the self weight of the wall at base, and what is the exact size that is required for the circular water tank at base. we have to compute that firstly. We cannot just put 1 meter. We'll check whether it is sufficient or not. So for this I will show you some formulas, and from that formula we'll compute the thickness required. So considering this as a circular tank, this is the plan view. So the water will exert pressure on this direction on the wall. So this is known as the hoop tension. That is, the wall tends to buckle out. So this is the hoop tension. We have to compute the thickness on basis of this hoop tension. So the basic idea, okay, let me draw the elevation view as well. So if this is the elevation view, okay, so this is the base and this is the circular water tank, and considering this as height h, okay, then the value of hoop tension is equal to Ft being the hoop tension, that is force. So basically gamma W into HW into diameter of the tank. So this is the formula to compute the hoop tension, and as we know this is 9.81 for water. Similarly height, okay, let us check the height first. The water level, here you can see the maximum water level is 1637.17. so we have to consider that 1637.17. so we get the overall height of the structure, sorry, water is 23.4. so 9.81 into 23.4 into 8.5 divided by 2, so 975.604, 975. But this is a static value, that is, as there will be the fluctuation of water height, so there will be the dynamic effect on the wall, or the dynamic force will act on the wall. So we have to consider that as well. Considering dynamic effect, dynamic nature is increased by 20%, that is dynamic factor as 0.2. so what we get is 975 into 1.2. so depending upon the horizontal seismic coefficient, you can take either 0.2, 0.1. so for Nepal generally the horizontal seismic coefficient, so this is for stability case, so dynamic effect will get this as 0.2. so basically this is 2 by 3 of PGA, and considering PGA as 0.3, so we'll get this as 0.2. Hoop tension considering dynamic effect is equal to, let us multiply this by 1.2, so 1170. this is the dynamic hoop tension. Now with respect to this, we'll provide the thickness, and before that we shall also consider certain percentage of reinforcement. So for computing the area of steel, we have a simple formula. AST is equal to Ft by sigma St. For hoop tension, or the area of steel required will be equal to hoop tension divided by the permissible tensile stress under direct tension. Okay, so we computed this value Ft as 1170 divided by sigma St. so basically this is permissible tensile stress, and you can find this in IS code IS 3370 part 2. Tensile stress in member under direct tension for high strength deformed bar, so obviously we'll be using Fe 500. so for this sigma St is 130. so coming back to this, taking this as 130, so this is in kilonewton and this is in Newton per mm square, so converting this into Newton, so area of steel required is 9000 mm square. Now we have to compute the thickness of concrete, or the thickness of concrete lining required. So for this also we have to use this formula. Sigma T is equal to Ft by AC plus MAST. So basically we are using working stress method, so we have to use this modular ratio here. I already explained about modular ratio in a video related to crack width, analysis of crack width. I can go to the description, you can find the link and you can understand about the modular ratio, why we are using modular ratio. So we know the value of sigma T. This is the permissible tensile stress in concrete. this is the hoop tension. Area of steel is just computed, and modular ratio can be computed for M25 grade of concrete, for particular grade of concrete. And similarly AC, this is the area of concrete, and AC is simply AC is equal to B into D, or we can just write A into B into D, gross area of concrete. And for sigma T, we'll again go to code IS 3370. So as you can see here in table 1, permissible concrete stresses, and permissible concrete stresses, here you can see direct tension, and for M25 grade of concrete we have 1.3. And don't get confused with the value of direct tension, that is permissible stress under direct tension. As you can see here 1.3 in this IS 3370, and similarly in IS 456 you will get this value, direct tension permissible stress in concrete, you will get M25 as 3.2. so this is without consideration of resistance against cracking. For resistance against cracking it is only 1.3. Overall structure is underground, then we can consider permissible stress without resistance to cracking, because in such cases cracking is not a significant issue, but structure which are, or surface structure are more critical, and hence resistance against cracking is to be considered. And for that we have to consider permissible stress considering resistance to cracking, and we'll take this value, that is 1.3. so now here if we cross multiply these terms, AC sigma T is equal to Ft minus MAST into sigma T. AC is basically B into D. Let me take, so this is 1170 minus modular ratio. So for modular ratio is simply 280 by 3 sigma CBC, and sigma CBC, for this again we have to go for IS 3370. in this case both the value are same, that is either from IS 456 or IS 3370, sigma CBC is same because it is for compression, and it will be same for both cases. So for M25 grade of concrete the value of sigma CBC is 8.5. if we put value sigma CBC as 8.5, then this value comes as 10.98. so don't get confused, this modular ratio is for considering partially long term creep. Substitute value of M as 10.98, AST which is 9000 into sigma T, this is sigma ST, this is sigma T, and we computed this value, or we found this value to be as 1.3 considering crack width, or considering the resistance against cracking, divided by sigma T comes down, so 1.3. we'll consider a unit width, so this is 1000 mm into D, this is in kilonewton, so convert this into in mm, and finally you can get the value of D, the depth required to resist this hoop tension without crack considering certain percentage of steel is 801 mm. so the depth required at base is 801 mm. so we have to provide minimum depth as 801 mm. For now let us assume the depth to be equal to 1000 mm at base considering other stresses as well. So this is for hoop tension only, so there will be other stresses, so to make sure that there won't be any other failures, so we'll provide depth as 1000 mm at base. So I have prepared an Excel sheet, and you can see that at 0 meter, or at level considered for design head 1613.77, so we are at this point, and we got the hoop tension as 975.6, and considering dynamic factor, the value came as 1170. Don't get okay. I'll explain this later on. And on basis of that, we got the thickness of lining as 802 mm, and we consider that the thickness, or we assumed as 1000 mm with this reinforcement. So this was at this depth. Now up to which depth will provide 1 meter then. Let us check at depth 4 meter. Okay, from this point we'll add 4 meter, so we'll get 1617.77. so level considered is 1617.77, and at this particular depth the hoop tension comes as 808.833 kilonewton, which was 975.60 previously, that is at the base. At 4 meter height it will reduce obviously, and with respect to that the thickness of lining come as 694 mm. Okay, we still assume it to be as 1000 mm because there is opening at this point, so the stress will get concentrated at this point. So we are providing the same depth, that is 1000 mm, to ensure that it does not fail under stress, direct stress. So we are providing 1000 mm, and similarly we'll check at other depths. Let us go to up to 7 meter. Okay, so that means 1613.77 plus 7 is equal to 1620.7. so this is the design head, and at this particular head the depth required is 562 mm. Now we have reduced the thickness, that is 750 mm. So beyond 7 meter I will provide thickness as 750 mm. You can cross check, I have shown you the process, you can compute the value and check. Okay, so 750 mm, and similarly I will provide that depth to a certain depth or to certain height, and then I'll again reduce it on basis of the hook tension at that particular point. So what I did is up to 7 meter, as you can see here, from base to 1620.77 I provided 1000 mm thickness. Similarly for the next 5 meter height I provided 750 mm, and then I have provided 500 mm, and finally 300 mm. Why 300 mm? This is the minimum depth that is to be provided as per the code, and at the top I have provided 300 mm, considering that it will be a 2-layered structure, that is the mesh or rebar will be provided in 2 layers, so it will be easy to provide, and will provide that because at the top there won't be any force acting, so nominal reinforcement and sizing will be sufficient. But to ensure that nominal reinforcement, certain depth of concrete will be required, so I am providing 300 mm, so it will be easier to bend bar at the top. I'll explain all this value how it came, just I am showing you to calculate the dead load of the structure. So now let us go to this, and as I said, at bottom we have wall thickness of 1 meter and the height is 7 meter and the radius being 5.25. How? 4.25 plus 1, because the internal radius is 4.25, and if the thickness of wall is 1 meter, then it will obviously be 5.25. Okay, let me show you here. So we have a inner radius as 4.25 meter, and the internal thickness of wall is 1 meter. So we are interested to find this volume only. So obviously we'll reduce 5.25 minus 4.25, that is 1. So pi d square h minus pi d dash square h. So firstly the diameter is 5.25, and in this case it is 4.25, and we'll get this much area or this much volume considering h. So 208.92, multiply this with unit weight of concrete 5222.9. Similarly there is opening, as I said, and the opening here is a circular type and the radius of the opening is 1.15, and we can simply get the volume as pi r square into h. In this case, the height will be the thickness of wall. Multiply this with unit weight of concrete and we'll get 103.87. As we are going to subtract this, so we'll put minus sign. Now the next wall, that is, or the next section of wall, that starts from 7 meter from the base and is extended up to 5 meter. Similarly, the radius will be 5. Obviously the thickness is less, so the radius will also be less. And similarly we can compute all the wall or the total weight of the wall. Finally we have slab. Let us assume the thickness of slab as 1.4 meter, considering that there is no any failure. So this is an initial guess, so I'm just putting 1.4. And the internal radius, overall radius, let us assume as 7.75. So this overall diameter, as you can see here, internal radius of the surge, or we can say tank, is 4.25. Thickness of wall at base is 1 meter. So the external diameter as base will be 10.5. So 4.25 plus 1 into 2. So that will give the external diameter of the base. And projection on either side. Since because there is load acting, so we'll see whether there is requirement of projection or not. Okay, for now let us provide projection as 0. So the provided overall diameter of the base slab is 10.5 meter. And the radius will be 5.25. So overall volume pi r into pi r square h. So we get 121.23. Multiply this with unit weight, we get 3030.66 as the volume of slab. Now finally we have water load that will act on the slab. So as I said, the height of the water, considering maximum of surge. So this is the maximum volume of water that will be accumulated in this tank. So we will consider this weight. So 1637.17 minus 1613.77. So this comes as 23.4. Internal diameter 4.25. So pi r square into h, we get 1327.83 meter cube. And multiply with unit weight of water 9.81. So this comes as 13,026.05 kilonewton. Now add up all this value. Total load is 28,285.43 kilonewton. And the area of base, which is simply pi r square, 5.25. Okay, and this is 86.59. So what will be the intensity of soil pressure then? Total load divided by area, 326.66 kilonewton per meter square. And we have allowable bearing pressure as 200 kilonewton per meter square. So it obviously exceeds the allowable pressure. So we have to provide projection. So let us provide projection of 2.5. So this comes as 168.84. Let us provide 2, 187. Let us provide 1.5 on either side, 209. Let us provide 1.75, 199.06. So a projection equal to 2 meter will be sufficient to satisfy the bearing pressure of soil. So in this way we have just computed the bearing pressure of soil. So in this way we have calculated the base width of the slab. Now we'll go into the molding. Now let us go to SAP. Okay, so this is what we are going to model, and I just wanted you to make clear about the sizing of the base plate, and now we'll model. Okay, so now let us go to new model, and for now let us go to blank. The first thing, we'll define materials. So add new material, India concrete M25. Add new material, India concrete is now we are going to define rebar and 500 grade. Okay, so material defining is done. Section properties, so we'll define area sections. Add new section. So firstly we will define base slab, and the depth is 1.4 meter. So thickness for membrane 1.4 and thickness for bending 1.4. So basically this is about the property modifier, but for now we'll provide same, that is 1.4 and 1.4. Material name M20 and other things. That's why, so we are not going to design using SAP, so it doesn't matter if we redefine these things or not. Okay, so only thing we have to consider here is material M25. So if you want to modify anything over here, we will not modify for now, and it will be cell thin. Okay, similarly add copy of section. Now we'll add wall. At base we have 1 meter, so 1 other things will be same, and this is wall 0.75 0.75 0.75. Add copy of section, wall 0.5 0.5 0.5. Add copy of section, wall 0.3. Okay, so we have defined area sections as well. Now load patterns. So the load cases that we are considering for the analysis of the tank is the self load, that is the self weight of the structure, which will be the dead load. Similarly weight of water and the pressure due to that water, internal water pressure, and the active earth pressure, live load if there is any, external water pressure from the ground, that is groundwater table, so that pressure will be induced and will act on the external surface of the wall. Similarly upthrust, that is uplift acting at the base of the slab, and earthquake load along both direction. So these are the load patterns that we are going to define. So self weight multiplier will be 1, and another load is live if there is any. Add water load, this will be dead, but self weight multiplier will be 0. Add new load pattern, water pressure, or we can even use same, not need to define twice, and earth pressure, EQX, this will be a quake type, so add new load pattern, and similarly EQY, add new load pattern, and finally there is uplift, and this is dead, add new load pattern, and we'll add the dynamic water pressure as well, so this will be 0. Okay, let us modify this. Modify. So these are the load patterns. Okay, similarly load combination, we have to input this manually, and I'll do that later on. Firstly we'll model the structure. Right click and go to edit grid data, add new grid system, because this is a circular structure, so we have to define circular grid. Go to 2D and OK, and go to quick start. Cylindrical, we'll choose this one. So number of grid lines along radius, along theta, along z. So I'll explain this. Firstly just press OK. So here you can see along radius, so this is along radius, number of grid lines 4, so 1 2 3 4. Along theta, So this theta is with this angle. So here is 7, 1 2 3 4 5 6 7, and along z, that is the radius, sorry, along the elevation, so that will be a different thing that we cannot see in the 2D frame or 2D view. So along radius, how many grid lines will be important or will be necessary for us? So here you can see from the drawing as well. So considering this as the origin 0 0, so we'll require 1 2, so 2 grid lines along radius will be sufficient for now. And similarly along theta, for now let us go as 14. Along z, so 1, so we are providing 4 different heights. So considering base as 1, 750 as 2, 500 as 3, and this as 4, so 4. Grid spacing along radius, internal radius is 4.25 and external radius at base of wall is 5.25. so we'll take average because we consider center to center dimension for the structural modeling. So 4.25 and 5.25 will get 4.75, and we have along theta. So for now let us put this as 15, and if we divide 360 divided by as 15, we get 24. So 24 number of grid lines along theta. And along z, okay, for now let us go as 7. First grid line location 0 0 0. Okay, now firstly we'll model the base slab. Okay, coming to xy, so this is basically 4.75, and let us draw a frame. So it is quite little bit tedious to model circular elements in SAP, so I wanted to make you learn these things as well. So now edit, go to extrude lines to area, and we are going to extrude this or convert this into area in a circular way. So go to radial, put this as Z, and we are going to extrude this into slab. So we'll select base slab, that is the property that will go apply to the slab. Rotate about 0.00. Angle, so we had the grid spacing along theta as 15, and the number, so basically 360 divided by 15, 24. Total rise 0. Delete source object, will delete this frame. So right click, okay, go to display option and select fill objects and go with color printer, apply. So here you can see that this red color and this is gray color. Okay, you might see a different color if we are having classic plus. So in this case it will be red and it will be, and the other color will be magenta. Okay, but for now I am selecting the DirectX view, so I'll get gray color. So what is the significance of this color? So red color means the top surface of the structure, and this as the bottom surface of the section, better to say section. So red means top surface and this means bottom surface. And considering the water will be inside the structure, so I'll try to make the surface that will be in direct contact with the water as the bottom surface. So for that, what I have to do is, if you remember what I did before drawing this element, so I drew from this point to this. So that means, okay, let me show you once again. So if I'm selecting from this point to this point, so basically here the extrusion is being in anti-clockwise direction. So if we see in this direction, then if we are drawing anything, or the if we draw any element in anti-clockwise direction, then it will show red color, that is the top surface, towards us. So for now, if I want to have bottom surface towards me, then I have to draw this frame element in clockwise direction, that is from this point to this point, and the extrusion will be in the clockwise direction. So let me delete this, and I'll draw from this point to this point. Now let us extrude this. So you can see the shortcut key over here, extrude lines to areas, and other things will remain same. So now you can see the bottom surface is facing towards us. So now it will be easier to apply load, considering that water pressure is to be act in the internal surface of the section. So first you have modeled the bottom slab. Now we'll draw the wall element, and then we will provide projection for the base slab. So what was the height of the structure? 25.4, and for now the value of R is just 21. So now let us go to it is grid data, and in C system, so this is the added system, so modify, and we'll put this as 25.4. Other things are not necessary for now, or we can also go as 7, and 750 will be provided for 5 meter, so that means 12, and finally 500 mm was provided for 444, so 11 meter. So 11, 12, 23, and it was provided for 2.41. Okay, reorder ordinates. Okay, now let us draw frame element first, and we'll just extrude those into lines. You may find other ways to model cell element also, but this is how I model cell element for a circular grid. So again, as I said, the inner face should be, or the water surface will be acted on the bottom surface, so we'll tend, for now the red surface should be facing towards us, that means anti-clockwise. So if I draw from this point to this point, let us select this line up to this point. So this will be for 1 meter wall thickness. Now let us extrude this. Other things will remain same, the only difference will be the property for added object. Okay, so as you can see, top surface is facing towards us. Now let us do the same thing for wall for of 0.75 thickness. So again from this point to this point, and we'll extrude this considering 0.75. Now for 5 meter, 0.5 meter thick wall. And finally for 0.3 meter thick wall. Now let's go to extrude, and you can see the extruded view. Now we'll provide projection for the slab. So how we can provide that then? So we'll add a grid along radius, and we'll extrude a frame line in the same way. Edit and go to this, modify. So 4.75, and what was the overall diameter? 14.5, that means 7.25. So let us add 7.25. Okay, now go to XY and at Z is equal to 0. Again we'll draw a frame and we'll draw from this direction to this, and we'll extrude base slab. Okay, so there shouldn't be any problem now. Okay, the video looks to be a little bit longer if we try to complete this in a single video. So I'll try to explain this in a number of parts of the video. So for today this much, and if it did help, do like and subscribe our channel and leave a comment. Thank you.